Hello, this is Hassam Kucheki. Welcome to this video. In this video, we are going to talk about my bachelor's project about image captioning. In this video, I assume that you don't know anything about image captioning at all, so I start at a very base level to reach the higher level of the image captioning. Well, first of all, what is image captioning? Image captioning is the task of giving an image to the model, and the model gives us a sentence which appropriately describes the contents of the image in a correct grammar and, of course, words. Uh, you can see the image of this task. For example, this model is given to the model, and the model outputs the two young girls are playing with the Lego toy, or for example, for this one. Let's dive into how the structure of these models are. Uh, Let me write in the board. First of all, we have an image which is here. This is our image. We want to give it to the model, and model gives us the caption. Uh, For example, it's inside of this. Uh, what we need to do is that we give it to the model. Uh, uh, at the very first level, we have a CNN layer. What is the CNN? CNN is convolutional neural network which processes the image and uh, determine which objects are appeared in the image. So we have the image here in the dimensions of 299 times 299. We give it to the CNN, and CNN outputs uh, an array with the specific dimension. For example, we have various types of CNN like VGG16 or Inception V3, which is used in our project, or AlexNet, and etc. For example, each of them are varied in size in both input and output size. For example, VGG16, I think it inputs the 2 to 4 times 2 to 4, but Inception V3 has a higher dimension, which is kind of more accurate in detecting objects. Well, these are CNNs with a specific input size and output size. For example, in Inception, uh, when we input this image to the model, this gives us a 1 times 1000 element array. Okay, and this is the task of classification of this image. For example, that says this is an bicycle, for example. It doesn't tell us how many objects are in this image. Just tell us one class, which is this image is mostly about, and others are, for example, less probability of the appearance in the image. For example, a car has the probability of 0.4 in this image, but for example, a bike has the probability of 1, which is a softmax applied to this array, and 1, which is related to the bike, is output force. But we don't want this CNN network to classify this image. We need the object detection task. So we ignore the last layer, and after that we need the one before last um, layer, which is in the dimensions of 1496. 1496. This means that Inception v3 can detect uh, 4096 different objects in the image, and each of them has their different and varied probability. For example, this can say um, there is a car with one with zero point 0.4 probability, or a house with 2, or a pen with 6. Uh, since we can output a 4096 dimension array from this network. When we got this is called, let me type it here. This is called feature vector, as it represents the uh, features of this image in a vector. So we have it, and all of these, all of this code is called encode or encoding, as we are kind of uh, encoding an image into a vector representation, and such a task like image captioning is mostly called as an encoder decoder task. Uh, this was the encoding, and now we want to explain the decoder. After the CNN detects how many objects and what objects are in the image, this passes this feature vector to another layer, which is mostly LSTM, long short memory, or other types of long short memory, other types of recurrent networks like RNN or GRU. Gated recurrent unique recurrent neural network, and LSTM, long short term memory. Uh, all of them are used to predict sequences that are related to each other at each time steps. Uh, one is related to its previous elements. For example, when we want to create a sentence, the fifth word is related to all of previous words. So here we need to use GRU. Why GRU? LSTM has lots of gates, forgot gates, save gates, remember, all of these various gates, and uh, needs a lot of computational uh, processing and lots of space for storing its cells, and as a result it requires a lot of RAM and uh, CPU to process, so it's not suitable for faster training. Uh, Also, recurrent neural network or RNNs are weak in remembering the very first words, especially when the sequence is becoming long and long. For example, this is a sequence with, uh, for example, 3 words. The first word is don't. When we go through and reach the 25th word, RNN is most likely to forget this word don't. And by forgetting this word, it means the meaning of the sentence is actually reversed because its don't is forgotten. So we can't really trust to RNNs to produce long sequences of words. So we need to use GRU. GRU is something between LSTM and RNN. It doesn't have the forgetfulness of the RNN. It can remember longer sequences, and also isn't that much complicated as LSTM and is faster in training and using. So in this project we use GRU. GRU, given the feature vector, creates a sentence which is the description that describes the first image. For example, that can say a little girl playing in the, for example, field. And uh, this is called decoder, as it decodes this feature vector to human understandable words. And this is the whole process that is ongoing on the image captioning task. Let's dive into more details. Okay, now let's check the project. In this project, we use the Flickr 13K, but this one is 8K, and this preserves the output of the cells, but here it doesn't. So we're going to use this, but both of them are the same, just dataset is changed. In the first cell, we import different libraries. We define paths. We load all images in the dataset, and here we can plot some image, the 10 recent, the 10 last image of the dataset. Here, as I mentioned before, we resize them into a size of 299 and 299. Here we can read the dataset from caption file. Caption file is a CSV, which is um, formatted by the name of the image, a comma, and its caption. Um, I need to mention that the dataset has 5 different captions for every single image. So here image is the same, but captions are different. And as you can see here, we have 4,000, almost 4,000 image, which is gathered from this calculation. We have 8,000 image, and each of them has 5 captions, so it sums up to for about 4,000. And when we unique them, we have 8K unique image and 4,000 image unique captions. Here we plot again, as I said before, we have 5 different captions per image, and these are the image. Here we can clearly see that images are in different sizes, so we need to consider resizing them into a single uh, fixed shape. Here we read the captions, and here we just unique the captions, split them, and actually read the caption file and save that into the data text. This is the result. We have 5 captions per each image. This is again the data frame with this size. We have 3 rows, one ID, which is the name of the image, path is the full path of the image, and caption is the caption related to that image. And here we can again see the captions. We can look at the first 10 captions. Again, this is repetitive. Here we just create the vocabulary. Uh, in the word, we can process each caption, split the words, and put them into the word, and then return the sorted array. Here we just rename the dataset, data frame of vocabulary. Here we can plot the top 30 most frequently appearing words, we can see A is very frequent in each word, and this is 60,000 words. You maybe wonder why when we have 40,000 captions, but we have 60,000 occurrences. That's because some sentences may have more than one A in there. And if you saw this, I used to remove A and into from the uh, word list because I believe that that could lead the model to have bias about creating the A as it's too frequent in the dataset. Here again is image. We can here use this function to plot image with their caption. We can see this image as this caption, and here you can notice the start tag and end tag for the image, which is uh, going to be explained later, but we do this for all of them in the data frame. Again, here we have the vocabulary, we have data limiter and tokenizing. Tokenizing is uh, is a function to remove these special characters and put the UNK, stand for unknown, instead of them. As they are not very informative, we don't really tend to uh, teach the model to predict them. So we just remove them easily and put this special character instead of them. Also, we need to create a word to index and index to word. Uh, I need to explain two things here. These two and what is the padding. As you can see here, we put the end and start uh, at the first and the end of each caption. This is used because when we uh, work with neural networks, we mostly work with tensors to the array. So when we put the first caption, which is this, and second caption, which is this, and the third, which is this, uh, we have extra empty space here. Okay, so the first sentence might be 5 words left, and the second one maybe have 10 words. Uh, they can't easily fit into to the tensor, so we put a special character at the end of them to make them have the same length. So this is the padding. This is a padding, and we, if I can show you, I can't find this. Yeah, and this is the first caption. We add lots of padding to be at the size of 35 as the longest sequence available in the dataset. And if the next caption has a longer length, it doesn't produce any problem because it is filled with this padding. So this was the padding, and that was the padding. I need to explain word to index and index to word. Back to here again, when we have uh, extracted features from the image, they uh, stored in an array with an index, which is, for example, this is car. Okay, we don't store the car here and the probability with it because of two things. First of all, car has three character length and may waste a lot of space in the memory. And the next problem is that neural networks are working only with numbers, so we can't put any categorical word or any word into them and feed them into the network. So we just replace them, and we say the model everywhere you see the number 3, it's related to car. And everywhere you see the number 4, it's related to, for example, bike. Everywhere you see, for example, 15, is related to house, for example. This is a vector which is map the index to the word, which is called index to word. The reverse thing is called word to index. Word to index is used here. We have car mapped to an index, Uh, this is uh, word to index used in encoding. Index to word is used in decoder as we has had this feature vector and the LSTM or RNN or GR. You predicted a few words, for example, the word 4, the word 17, the word 40, predicted these numbers, and we want them to be in a human understandable sequence of words. So we need to convert them back to their original words. So here we need to use an index to word list. Here we just create that index to word and word to index arrays. As you can see, padding is the uh, index 0, and everywhere we see 0, it means it's related to padding. So this caption is just mapped to the index, and this is the paddings. These are the paddings added to make it to the length of 35 to be in a shape that is feasible to the network. And that was the task done here. Mm, and here the length of caption vector and max length of this caption. Max length of the Flickr 8K is 35. The Flickr 30K max length is, I think, 74, if I'm not mistaken. Anyway, here we can see the index for the start, the start which we added to the beginning of the caption is 2, sorry, is 3, and padding is 0. And this is also index to word. The index of the 5 is related to the the word in, and the index of 4999 is related to the word somewhere. Here we just have the counting of each image in the vocabulary, and this is the pre-processing. This is the processing of captions. I need to explain the start and end. Uh, as I said here, the model learned to predict some integers as they are representation of some words. Uh, we need to specify when to start a caption, where is the start of the caption, and where is the end of the caption. So when we need to start a caption, we just, instead of giving an empty uh, empty string to the model, we just give an start. So the model understand it needs to start generating sequences, and when the model produces the end index, it means that the sentence is end, and further we can see in the code we handle the uh, exception when the model uh, predicts the end, and we just return the created sentence with all things between the start and the end. So a start and end are just two things to handle these sequences. After pre-processing the captions, it's time for pre-processing the images. So here we just import the pre-trained Inception v3, and as I said before, we don't need the very last layer as it's a classifier. We need the one before the last one layer, so we can have the features extracted with this by this model from the uh, image. And also we have this pre-trained to save some RAM and resources, uh, that's pre-trained on ImageNet. Here we define that this is a preprocessor image function. We make them a unified shape, read file, decode that image into a channel of 3. This 3 is because RGB. We have 3 color channels. We resize them into the image shape, and we gives the image to the preprocessor input function of inception theory, and return the image and its path to the color of the function. Here we define the batch size, again the size, and here we encode them into the batches. Uh, we map the image data set using the preprocessor image function, and uh, this parallel, which is auto-tuned by TensorFlow, into the batch sizes of batch size, which is here 128. We can here check the sizes. We have a 128 batch size of this image with 3 channels, and this is also the captions corresponding to each image in this uh, tensor. Here, this is the most error prone part of uh, almost all of the projects I uh, checked, and this is error prone because they need to take care of the shape of dataset and the format of the dataset, which is stored in the uh, program. Now I want to explain why this is wrong. Let me open a new pane. As we saw before, here uh, we have the image ID with its corresponding caption. So dataset is in this shape: image 1, caption 1, image 1, caption 2, image 1, caption 3, image 1, caption 4, oh my god, not image 1, image 2, caption 1, image 2, caption 2, and so on. So we have this dataset. Uh, we we need to uh, we know all of these are related to each one image, and this is the next image. What this code here does wrongly is that it just randomly picks some of them and keep this for terrain and keep this for test. This just put these samples with the rate of, for example, 2. We just split them and put them into the test dataset. The fundamental idea of the splitting terrain and test is that we want to avoid and prevent model to see the image, some samples, and use those samples to test the model and check if it, it is working nicely or not. Uh, by doing this in an image captioning task, uh, we are just preventing the model to see a few captions of the image, but still the model sees those images into the training uh, process. So when we are testing the model using image 1, the model has seen the image 1 during the training, which is create uh, extremely high rate of evaluation metrics, which is quite wrong. Uh, what we need to do is that um, have a list of all of images and just cut some of these images, not this dataset. So this is the correct. For example, here just we cross out these two images and put them into the test. So this is quite wrong, which is done into lots of projects I have seen before. This doesn't technically done in this project. Later we can see the correct. Here we just process the image, the whole images with this byte size of is equal to 8K. Uh, just here we extract the features of each image before training time, because this can save some time during the training. And this is again the image to caption vector, which is appended here. And here we have vector to sentence. Here is the corrected part of the dataset, splitting dataset. Here we just need to set the random seed. This is important because here we just process all of the images. So we need to always put the same exact samples from the model, because when we once train this model, we later can load the pre-trained model and don't run this part. So we need to exactly sample the specific image instead of every random time, because this again can cause this problem to we pre-train the image from this group of image, but the next time when we shuffle them, uh, some of these elements might move to the test subset or stay in the train subset, which is can again make the previous problem I have discussed before. So we need to set a random seed and just slice them. We can use the slicing because we shuffle them, and correctly here we are going to split them. And after checking the sizes, we can see the dataset is split quite nice. And here we have some other functions. I showed I've shown this part to you. We have a start, caption, end, and padding to have the same length with other captions. And here we plot two images again. As I said before, we showed the pre-processing with inception v3. Here again is the batch size. We are here creating the train and test datasets with shuffling and fetching using batch size of 128. Again, do this for test dataset, and here is the batch size of uh, train and train image batch and train caption batch. Again, here we check the values, which is correct. Uh, Here we can see the 128 size of batch with 35 captions, and this is the size of uh, features, which is decreased, which is divided by 2 to uh, lowering the dimensions of the features. And here we have the padding mask. We have the lookout mask. These are used in creating attention. Uh, all of the math are related to gathering the output and attention weight to be used into the multi-head attention layer. The multi-head attention layer is used into the attention layer which is defined here. Uh, Again, we can have the implementation. We're going forward, and this is encoder layer. We dropouts is used to avoid overfitting the model that prevents the model to be linear and be overfitted as a result. Um, and here we can have the function call. We have here the decoder layer, which is used the multi-head attention layer again. We have the dropouts here also, and we have the attention weights. After that, the encoder again, we use the ReLU function, activation function, and also uh, this is created the mask and returns this. In the decoder, uh, as I said before, we have used the previous class, and uh, you return the X and attention weights. And this is the encoder layer which made use of uh, previous defined classes. This is the attention model. With all of this implementation, you can see and read all of them. We are not going to go deep into them. Also, we need to reduce some in the axis 1. Here we can see the context vector with the attention applied. The attention model is returned. In the decoder, we have GRU as I defined and discussed before, and other things. This is just return X state, hidden state of the GRU and attention weight to be used in future tasks. Here we define the encoder and decoder. The features are uh, storing results of encoder, and here we can see the size of the outputs of those models. And here is the final model which just used the previous defined model and just do the task we want. Uh, this is a custom scheduler which is used in the Adam optimizer to have the learning rate dynamically changing. Uh, we use a sparse categorical cross entropy because uh, we need to uh, make the model predict integers, and this is one of the greatest and most appropriate loss function to for such a dataset. And you can see here um, if I can find that optimizer. Yes, that's here, I think. Yes, here I fully defined why this categorical cross entropy, especially sparse, is is a great choice for this kinds of task. And uh, we can read this and go through this decision. After that, we defined a loss function. We also here defined a checkpoint that we can restore the pre-trained model, or sometimes if the training is stopped due to some problem, we can restore that and continue from that checkpoint. Here we can have the checkpoints restored, and this is the train step. As we are using attention and other kinds of stuffs, we need to define our own train step. This is the training step, uh, and these are the defined. These are the uh, word by word, and this is the uh, one-to-one sum, which is, and here we apply the gradient. We calculate the gradient, and here we apply the gradient. And this is also the test step, and this is the test loss calculation. Uh, Train loss is calculated using the mean of all of the train losses, and this is the training step. Here we use 25 epochs for Flickr 8K and 15 for Flickr 30K, as that doesn't fit into the RAM for larger epochs. Um, the training is done here, and we save a checkpoint whenever test loss is less than best test loss. We save that checkpoint and plot the loss. We can show you loss plot after 50 epoch. 50 epochs is look like this. And here we reach the model evaluation uh, using grid search. This is the evaluation for I in max length. Well, I need here to describe another thing. Um, I think I missed something uh, that is worth explaining. Yes, here in the train step we have this teacher forcing. What is teacher forcing Apple? Well, let's assume that we have a caption. Where are your captions? Oh my god. Okay. Imagine we have this caption. Okay. Let's assume we have this caption. When we want to feed this to the model, we are going to do such a thing. First, we give the start, then we give the start and a, then we give the start and a and little, and then we start leader girl in, and so on. Well, we feed the model just like that. Okay. Uh, when we want to have the model predicting such a thing, in the training steps, we ask the model to predict this word, for example. Okay. And now the model has predicted a start a little. Okay. Now for the next word, the model should predict the word girl. Okay, but if the model is mistaken and instead of girl just predicted a word like boy, this can lead the whole sequence to be corrupted as this word is completely wrong. Okay, so that completely ruined the training step, especially for this specific sample. So here, when the uh, model mistakenly predicted the word boy, we just cross it over and put the correct word girl instead of the wrong word. And this can help the training process to be very fast as we are avoiding the whole sequence to be corrupted by just a single uh, incorrect or uh, not appropriate word. So when the model in the training step predicted a wrong word, we just cross it uh, out and put the correct word. As we know here, this is girl, uh, and let the model to uh, keep producing the next sequences. So this is the teacher forcing uh, which is done here. And in that code, in that part of the code, uh, here, we also checked if the predicted word for the I in the max line, if the predicted word is equal to end, it means that we reached to the end of the sequence and just return the result plus attention plus prediction. So this is the task of uh, predicting y by one each of these words. Here we have a function to plot attention map. We are going to see them not here. Ah, uh, attention task is to uh, keep an eye into specific areas of the image instead of looking at that as a whole. And this is done when we are here. Okay, we have the feature vector that extracted features of this image from different parts of the image. Okay, uh, and let's see, we have these, and we have this. Okay, and these are the features that are extracted here and stored in the feature vector. What the attention does is that actually created a vector with different coefficients. For example, 1, 2, 3, 1 again, 9, 8, 1. When this LSTM or RNN or GRU looking at this feature vector and try to predict a single word, all of them have the same weight as the GRU or LSTM looking at them and can create words based on them. But when we multiply this attention vector with this feature vector, we are just fading some of these objects away and force the model to look at specific parts of the features that are extracted here. For example, with this attention method, we ask the model to look only at only is about hard attention, mostly is about soft attention. Here we ask the model to mostly look at this part of the image. And for example, in this time step, the model uh, predicted for example, circle, which is here circle. At the next step, we using this hidden state and the previous attention weights, we reform this attention vector. For example, now we put the 9 here. Okay, now the model is going to uh, have an attention over here, and here might be related to this part of image, and now the model predicted this shape. And the next time, for example, we have the attentions here and the 9 is now here, we also cross it out, and now the model would have an attention over here which is related to here, and now the model using this and this attention vector using this feature vector predicted the shape of the scroll. And I need to mention the changing of this weights is also related to the last hidden state of this decoder and the uh, current weights available in the feature vector. This can use the model to create better words than the uh, situation without using an attention vector. And here you can see the attention map. For example, when creating the word A, the model was attending to this part of image, and at the next time the model was attending to this part of image mostly, and here, which is here, is meaningless, and here there is a man, so the model predicted the word for the while the model was predicting the word cleaning, it was attending to this part, and you can see the rest of it. And you can see here in a bad example, bad prediction, you can see it predicts lots of unknown words for this image. And here you can see when it's predicted the word hockey, that can see the shoes of the players, and also here you can see the players. That's kind of cool. And this is the other example. We can see clearly the attention map. Here we can produce an image with captions and results, which are exactly this output. Here we calculate the value score and meteor uh, with different weights. Here we can see the results. Here we could get these results using this sample count. and just save the model. And here is the uh, code for calculating the meteor for the whole corpus. I can't find anything more to explain. I think I have covered all of the subjects here. So, uh, yes, I just explained everything. I hope it helps. And if I found anything more to explain that I missed for now, I would make another video for that. And that's enough for now, I think. Hope you enjoy. Take care. Goodbye.